so I think we're just going to start. So, first of all, I'm going to start off with asking you a few questions. I promise you, these are going to be the only questions I'm going to ask you, because I know it's horribly embarrassing having to raise your hands like, you know, someone normal. Who would say they know at least the basics of functional programming already? A couple of you. Who knows about monads? Wow, someone actually raising their hands. That's impressive. Right, so what I'm going to be doing today, basically, is going through the language of functional programming. I don't mean like a functional programming language. I'm going to talk about the concepts and what they mean. But first of all, I mean, this is a talk intended for hipsters. So I'm going to try and explain this to you in a way that will let you use these words to confuse other people and make yourself look smart. So I'm just going to give you some background first. I've counted 4 great paradigms of programming, and I'm going to run you through them right now. First of all, we have the systems programmers, using languages like C, invented, incidentally, by this guy. On operating systems like Unix, invented by this guy. He also invented regular expressions. This is called the procedural paradigm. It's basically, it started out with Fortran in the 50s, where people were just writing sequences of instructions and the computers would just perform them. Very, very low level. Then you have the object-oriented paradigm. I'm sure many of you recognize the object-oriented programmers in their native habitat. I know I've been there. And of course they use languages like Java and C# and even C++. And the cool object-oriented programmers use Ruby, of course, because that is cool, so I'm told. Then you have the functional programmer. Now, functional programmers, they feel a lot smarter than the object-oriented programmer. They like feeling smarter. And that is the essence of what I'm going to try and teach you today. See, I love this quote. I mean, when you think about it, a monad is so obvious, right? So, finally, there's the logic programmer. And honestly, I don't know if our planet's quite ready for logic programming yet. But, yeah. That would be languages like, say, Prolog, which nobody ever actually uses for anything except people who are so smart. You kind of suspect they're not from this planet. But in short, to summarize, from the perspective of a proper hipster, a programming hipster, there are really only 2 categories. There's the functional programmer, who is smarter than you, and likes to at least point it out occasionally. And there's the muggle, who, yeah, has ideas and traditions about how to do Java properly, and, yeah, poor muggles. So, there's a language called Haskell, which is kind of at the heart of this functional feeling of superiority. Because, quite simply, Haskell is designed by mathematicians for mathematicians, and the vocabulary that gives us is quite impressive. I mean, even if you don't really understand it, you can throw words from this vocabulary into a conversation just to make sure that other programmers understand that you're smarter than them, even though you aren't necessarily. The field of mathematics that this vocabulary comes from is called category theory, which has, I mean, yeah, hipsters. So anyway, category theory gives us a wealth of confusing language, which I am now going to teach you. So first of all, I'm going to talk a little bit about how this function stuff came about. So I'm going to do a bit of history time. Oh, sorry. Cats are so mainstream. Let's try something new. Anyway, there was this guy called Haskell Curry. And you might imagine the language Haskell is actually named for him. Haskell Curry invented something called the lambda calculus. And the beauty of the lambda calculus is that it consists of nothing but functions. No types, no integers, no strings, no pollutants and that kind of sort. Just pure functions. Well, it also has the concept of nothing. So if you want to do Boolean logic, basically nothing means false and a function means true. And you can construct layers on top of this, because it also allows symbols to refer to functions. To kind of create something that works as a language. You can make it do addition, subtraction, the basics. It's you know, Turing complete, basically. But it is totally confusing. And it is totally horribly useless for actually doing serious programming, which is the beauty of it. It's just a low-level mathematical concept. And this guy, Alonzo Church, developed a typed lambda calculus on top of Haskell's original pure calculus. Because he thought types are cool, and we need types. So that became the typed lambda calculus. And this actually perhaps can be considered the first great schism between dynamically and statically typed languages. And Haskell did not like the typed lambda calculus. You know, all these types and things messing with my beautiful pure functions. We can't have that. So they disagreed about this, but eventually Alonso's, because it is definitely a lot more practical, became the one that we kind of based functional programming on. Now, the first actual programming language to come out of lambda calculus was invented by John McCarthy. And it is called Lisp. This was invented in 1958. In fact, McCarthy didn't intend, and this is the beauty of it, he didn't intend to create a programming language. He just created a more convenient notation for the lambda calculus. And one of his students, accidentally almost, wrote a compiler, or an interpreter, in fact, for this this dialect of the lambda calculus. And discovered that it actually wouldn't run programs. So that was how functional programming was born, quite by accident. So it is less of a programming language, Lisp that is, and more of an expression of pure mathematics, which is why, in fact, it's still very much going strong today. So let's just get started with the actual concepts. The core feature of functional programming is that functions are first class, which means that functions are values. Just like, you know, your primitive data types and collection types, functions can be assigned to variables, passed as arguments, things like that. And I'm just going to illustrate by using a very, very simple function. Oh, and I should tell you that I'm going to be using, of all things, TypeScript to show you the code. I figure most people know JavaScript in one form or another. So if nothing else, you don't have to write it. I'm going to write it for you, but I think you'll all be able to read it. I decided on TypeScript because as I was writing this, I figured that this is going to be a lot more easy to understand if we have type annotations, so you can see what's going on. So I'm going to explain the difference between JavaScript and TypeScript. This is how you define a function in JavaScript. And what follows is a TypeScript type declaration. It says this function returns a string. It takes no arguments. So this is straightforward, right? If you're confused about functions already, you can think of a function as a class with just one method, right? That is actually a way to do functional programming in Java. You have things like callable and runnable. Runnable takes no arguments, returns nothing. Callable takes no arguments, returns a value. And a function takes any number of arguments and returns a value. So when I call it, it returns, as expected, the string hello every pony. Now, a while back, I actually started doing this in Python. This was in the 90s. And accidentally, I tried calling a function without the parentheses, which denote arguments. And I discovered that instead of not compiling, it actually returns a function. That's first-class functions. The function is actually a value bound to the variable called hello. So you can do things like assigning it to another variable, and then we can call that variable, and it's the same function. That's first-class functions. Moving on to something more interesting and more confusing, functors. In some languages, functor simply means a function. In proper functional programming, or in category theory, a functor is, I think we have a definition. A functor is a collection of x that can apply a function f, x to y, over itself to create a collection of y. Yeah? Yeah. So I'm going to illustrate. What that means is that a functor consists of two things. A functor is a description of a concept which includes a collection type. We're going to be using a standard JavaScript list, an array list. And it also includes a function that maps another function onto each element of that list. And this is hard to explain. It's very easy to show. So I'm going to actually I'm going to call this function map. So we have the idea of a list and a function map that works in that list. That is a functor. So a map simply, you notice it takes an argument, a function as an argument. The function type is that it takes one argument and returns one argument of unspecified type. And it takes a list of any type. And it returns a new list. So we're going to start by building a new list, just by adding elements onto that list. So we need a for loop. This is your traditional Java C looking for loop. I is less than list.length, I plus plus, you all know this. So, quite simply, what we do is new list, push. And instead of just, if we wanted to write a copy function, we could do this. And just return new list. Let's try that. This is not a map function, this is a copy function right now. So we just pass it the function that I was going to, this is going to be ignored right now. And run it, we'll see that there's an exact copy of that list. Now, the function argument is called func. Suppose we call func on each element of the list and pushes the return value of func onto the new list. Now, we're passing it a function called caps, in all caps, because it's very shouty, and that makes it easy to hear. It simply just takes a string and returns the uppercase version of that string. Notice now, every element of the new list contains an uppercase version. So we've taken that function and applied it to the list. Quite simply, element by element, using that function to transform the list. And that is a functor. It's normally referred to quite simply as a map function, and the idea that it works on lists. But the list and the function together is called a functor. And a functor sounds quite intimidating, which is good. That's what we're looking for. Moving on. Another typical, this is not part of the functor itself, but another typical function that you will use on lists is called filter. Now we have a function called toCool, which checks, which takes a string and checks that the string does not refer to Rainbow Dash because she is way too cool, if you like ponies. So Filter, let's implement that. It looks a lot like the map function, except I'm going to write the code here. Now, instead of running function on running the input function on the value, I want, because this is going to be a Boolean function. As you can see, it returns a Boolean. So, if func on list.I is true, I can type that out for you. I know in Java this is not allowed. Like that. Then we add the actual value onto the list. So you can imagine that what this function does is it simply takes a Boolean function and calls it with the value that we're operating on. If it returns true, it gets to be in the list. If it returns false, it's filtered out. Let's try. Oh, incidentally, as I've had my first typo, we're doing live coding right now, you might have noticed. There is a live coding. I'm going to mess this up at some point or another. If you see me messing up, that's not me testing you. That's me making a mistake, so you tell me, okay? Good, thank you. So, let's apply the too-cool filter on our list of ponies. It contains Rainbow Dash, Pinkie Pie, and Twilight Sparkle, so we would expect that only ponies that aren't too cool are returned. Which returns Pinkie Pie and Twilight Sparkle. Yeah, that looks good. Now suppose that we just flip this filter and filters out just Rainbow Dash instead of everything that isn't. It filters out everything that isn't Rainbow Dash instead of filtering out actual Rainbow Dash. See, now the other two ponies are gone. That's filter. Now, reduction. This is the final part of this traditional set of functions that work on lists. We have map, filter, and reduce. Reduce. This is an interesting one. This is a bit more complex. The idea is that we take a function which takes two arguments. We take a list again, and we take an initial value, which is usually just initialized to nothing, or the first element of the list, but we're going to keep providing an initial value. And the idea is that for every two elements of the list, starting with the initial value, we call the function with these two arguments. And I'm just going to write this out, it's a little more easy to explain when you see the code. We start with having a result, which starts as the initial value. And we need a counter. And another list.length. Another for loop. Now, we are going to simply accumulate the return values of this function onto results. So the return value of calling the function with the current value of result on list number I is simply put back into result. So it's a sequential accumulation kind of yeah, that sounds frightfully complicated. So let's just run this. Because once you see what it does, it's so simple. Just the AND function, first of all. Anyone care to guess what this is going to return? Very good. This is working. Now it returns 5. So 2 plus 3 is 5. That's great. Now let's use the reduce function. The function is add. We're going to reuse our list of ponies, and we're going to use an empty string as the initial value. What's going to happen now? It simply adds them together, and in JavaScript, adding two strings means concatenation. So this is a string with Rainbow Dash, Pinkie Pie, and Twilight Sparkle without spaces, quite simply. So it's actually taken every element of the list and added them together. And it's even easier to see if you go like this. Let's use just 3 numbers for starters. It simply sums the list using the AND function. course, we can keep adding things, and it's going to, yeah, it's going to return the sum of them. And the initial value can also be tweaked. 21 plus 5 should be 26. Yeah. So that's reduce. Now, you probably, or most of you heard of this thing called MapReduce, which is used by Google and other fancy things to do operations on huge data sets. It is actually just composed of the reduce function. The idea is that while not all functions can be used to... Oh wait, I should start. Suppose that you have lots of computers and you have lots of data, and you'd like to split the data up and process it on these computers in parallel. Using the add function, because no matter what sequence you add these numbers together, they're going to return the same result. So you might as well chop this in half and run it on 2 different computers or 2 different CPUs on the same computer, and then just add the 2 resulting numbers together and you get the correct result. So this is a form of parallelizing data processing, really. Now, this one's going to blow your mind. Here's the reduce function again. Reduce is actually at the core of all of these functions. Map is a special case of reduce. Let me show you. If I write a function called ShoutingMapReducer, which takes a list of string as the first argument and just a string as the second argument, and returns a list of strings. What it does is it takes this list and it concatenates the uppercase version of argument B, which is just a normal string, onto that list. And we use ShoutingMapReducer as our reducer function on ponies. And we give it an empty list as an initial value, because ponies is a list. That's a map. What we're doing here is we're starting with an empty list. And so it's the first iteration is an empty list and rainbow dash. So we take a list with only rainbow dash and concatenate that onto the empty list, and we keep going through each element, and we're actually doing a map function instead of Now we can generalize this, and to do that we have another concept to introduce: higher order functions. A higher order function is a function that either takes a function as an argument, which means that you've seen a lot of high order functions already. But this is the interesting bit. It can also return a new function. So you can have functions that create new functions, essentially. So here's the ShoutingMapReducer again. And we can generalize this. We can make a function called MapReducer, which simply takes a function which takes one argument and returns any value, and it returns a new function, which is a reducer function, so it takes 2 arguments, and this function returns the same thing as the ShoutingMapReducer, except that instead of explicitly calling to uppercase, we call the function, right? This is getting to be a bit complex, because now we are creating a new function that we're going to use later in the reduction. So this is a generalized version of ShoutingMapReducer, assuming that we pass caps as a function, because caps does this. Let's see if it works. So we should be able to, first of all, let's just run map caps ponies. Oops, yeah. Why didn't I define that? All right, well, you know what that's going to do, right? So reduce ShoutingMapReducer ponies and an empty list. That should, yeah, that's what map should have done. But this is what you saw on the previous slide. Now let's generalize. Let's call this with MapReducer of caps. That should be the same thing, right? Let's just Try and run that. That's the same thing, except we didn't actually write a function that, we didn't actually MapReduce a function that is aware of being a reducer. We used MapReduce to create one for us from a simple function, like caps. So, that was a high-order function. Combinators. This is another awesome word that frightens people. So, a combinator basically is exactly what we wrote on the previous slide. A combinator is a function that takes another function and modifies it, returning a new function that does what the previous function was doing and something more. So the dumbest example ever, which you probably won't ever need to use, but it's easy to see what's happening. Let's, first of all, let's try and just, as an example, run the square function, which we have there. It takes a number and returns the square of it. So 5 times 5 is 25. Now, we have our super useful function, and 3, which takes it takes a function, of course, which takes a number, and it returns a number, like square does, right? And we return a new function that also takes a number, and it returns the result of the function we pass in with this number, plus 3. So we have a plus 3 combinator, in fact. We have a function that takes a function that operates in numbers and returns, instead of the answer, it returns the answer plus 3. Fantastically useful. But at least we can see how it works. We simply apply this to the function and then call the result as a function with the argument 5. That gives us 28. Now, you might be confused by this notation. We could just as easily have said, let's see, square and 3 equals and 3 of square. And then we can call that on 5. That should give the same thing. Oops, where's my typo? There it is. See, that was the simplest combinator ever. And you can do lots of interesting things with combinators, obviously, but this is really all you need to know to be able to use the word to frighten other people. So that should do it. I'm going to show you a slightly useful combinator as well, though. Suppose we have an object Pinky, which contains the name and the pony type of a pony called Pinkie Pie. So we also have a function called ponyType, which gives us the type of a pony object. Simply pony.type. So Pinkie Pie is a Pegasus pony. I know, very clever. That was my little trap. I don't usually put traps in my code. I put traps in my examples. Pinkie Pie is an earth pony, and it's good to know we have fellow bronies in the audience. So, now suppose that for some reason we also have Rainbow Dash in here. But as a result of calling a database or something, Rainbow Dash is not an object but null. What happens then? We get an error. Because we're trying to call type of null. And that isn't possible. Suppose we write a combinator that null checks for us. Null check. Func. I'm going to skip the type hints for now, because I'm afraid we're running out of time. So we return a function that also takes one argument. And if x is null, we simply return null. Otherwise, we return the result of function. Is that right? So this still gives an error because we haven't wrapped it yet. But suppose we do apply the null check combinator to pony type and then call that with dash. It returns null instead of actually crashing. And it still works with Pinky because Pinky is not null, so it goes through and calls the actual function. So that's a useful combinator. It's a very simple one, but one that you might imagine actually using in practice. Moving on, composition. Function composition is the favorite of many functional programmers. The idea is that you can combine functions together and apply them in sequence to a value. So, suppose we have a function called hi. Every pony. Quite simply. And we have caps. Yeah. So, suppose we write a compose function, which takes two arguments, function 1 and function 2, which we assume take strings, both of them, and return strings. So, we return another function that takes an argument. Let's just call it s, so we know it's a string. And we apply these in sequence. So the idea is that we take s and we call func1 on it, which will return a new string, on which we call func2 and return the result of that. So we kind of chain the functions together, right? So we can do this. We first call hi on every pony, and then we call caps on the result, which should give us hello every pony, shouty. So, I mean, it's important to be heard, right? We can also do this the other way around. What's going to happen then? Yeah, obviously, it's going to capitalize every pony and then call hi on that, so we get hello in regular case, every pony in caps. We just compose two functions. There are more useful examples. I don't care. You just a function composition, have a vague idea of what's happening. So, this is a good one. Applicative functors. I'm not actually going to explain the mathematical details of applicative functors, because I see we're a bit short on time, and we're also going to do monads later, which are way more awesome. But applicative functors do sound a bit more terrifying though, don't they? Monads just one word. Applicative even has 4 syllables to frighten off the muggles. So an applicative functor is like a functor, if you remember from like 25 minutes ago what a functor is. A functor is the idea that you can map a function onto a list. An applicative functor adds another function. I'm just going to show you that, which should tell you why I show you that. Which should tell you why I'm not going to explain this in too much detail, because this is serious business, implementing this map function. Now, I wonder if we have map. No. But you know what map does. And we have an applicative map function, which takes a list of functions, and we should still have hi and cap, so we're going to start out with hi. And it applies it to any number of lists of values in sequence. So this one should be the same as the usual map, except that instead of a function, it takes a list with one function. And it returns, yeah, hello, monads, Pinkie Pie, and Twilight Sparkle. Now, this is going to apply these functions in sequence, not as a composition, but one at a time. So we should get the result of hi ponies and the result of caps ponies. As you can see, hello and caps. Now, are you thinking this is quite useless? Yeah, this is a useless example. I've seen people do clever things with applicative functors. Clever things like confusing people and making them wonder why do we need this, but never mind. So, let us see what an applicative functor can do with more than one list of values. Suppose we have a function, hug, that takes two values, penny 1 and penny 2, and returns penny 1, hugs, penny 2, as pennies do, because they're very happy. Now, let's apply a hug to ponies. What happens? Hugs undefined. Because ponies takes 2 arguments. The idea here is that you can add another list of arguments. So now let's do more ponies. More ponies. So rarity, Applejack. My typing's horrible today. I'm blaming the speaker's dinner. And Fluttershy. Very good. Go bronies. So, ponies and more ponies. So you'd expect that Rainbow Dash hugs Rarity, Pinkie Pie hugs Applejack, Twilight Sparkle hugs Fluttershy, right? No. What happens here is... Sorry, I said a typo. What happens here is that every possible combination of these 2 lists is going to be applied through the function. So we get Rainbow Dash hugs Rarity and so on. We should have every possible combination of these 2 lists of ponies hugging each other, which is super cute, right? we can reuse the list of ponies as well. So they are hugging each other and themselves, just to make sure. That was an applicative function. Currying. Sorry about the unimaginative picture, but... Currying is, the act of transforming a function of several arguments into a chain of functions of 1 argument. That will yield the same result when called in sequence with the same arguments, as you can see, right? Good. Then we're done with that. Currying is also named after Haskell Curry. He's a very popular guy who thought he had discovered this concept of splitting up functions. Turns out it was really discovered earlier by some guy called Moses Schoenfinkel. So, if you want to be really hip about this, when talking about currying, you should be talking about Schoenfinkeling. Because even mathematicians probably won't understand that. Now, what is currying? What is currying? Because I'm assuming most of you aren't well versed in category theory. So that formula probably doesn't make much sense to you. The idea is, I have a curry function here. It takes a function and it takes a number called arity. That's a very useful word, which simply means the number of arguments a function takes. So the curry function itself actually has an arity of 2 because it takes 2 arguments. Quite simply, if arity is 1, we just return the function applied, essentially just return the function. Well, the function application, obviously, with a value. Otherwise, we recurse, and recursion throws people off. I'm just going to show you an example, yeah? Because it's easy to see what happens with the example. We have a function add, which takes any number of number arguments and adds them together. 1 plus 2 plus 3 is 6. Now let's curry that, see what happens. Let's say we're going to use 3 arguments. This takes any number of arguments, so we can just make up a number. But we were using 3, so let's start with that. What happens is that we get a function which takes 1 argument. Let's try calling that function with the first argument, 1. It returns a new function, which also takes 1 argument. Let's call that with the next argument, 2. Another function. Now, arity of 3, remember? So let's call that with the final argument, 3. That returns 6. So what we've done is we've broken up a function with 3 arguments into a function that takes 1 argument, that returns a function that takes the next argument, and so on, until you get the result. Why is this useful? I'll show you. Suppose we just call the 2 first arguments. That gets us the function. Let's call that 1 plus 2 plus something. and call that, sorry, care to guess? 6. So it's basically a way of pre-filling arguments. You can create a new function with some arguments already applied to the function that you're currying. This is called partial application. This is important to remember. Most people confuse currying with partial application. Partial application basically means that you take some arguments and you put them at the start of the argument list of a function and get a new function with these arguments pre-filled. That is a special case of currying. So if somebody refers to partial application as currying, you can now call them stupid. Congratulations. This is partial application, by the way, is in its simplest form. Instead of actually currying, I'm just using JavaScript trickery to create a function that concatenates the two argument lists together. So I can go partial. This is a bit easier to type, you noticed. Add 1 and 2, and then call it with 3, and it gets a 6. I don't even need to specify the arity, because that's implied by this. Oh, in fact, I can easily call it with more arguments, because AND takes a potentially infinite number of arguments. So yeah, 15, 1 plus 2 plus 3, that's partial application. Now, I think we're essentially out of time, so fortunately we have now monads left. Monads aren't difficult. Monads were invented by the only guy who didn't actually need any photoshopping, Philip Wadler. No, I lie. They were not invented by Philip Wadler, but he was the man who figured out how they were useful in computer science. Because Haskell, being a purely functional language, which means a language without side effects, means that it's academically beautiful, but you can't actually do anything useful with it. And Philip Wadler discovered that using monads, you can actually cheat and have side effects in a language with no side effects. So monads are magic. There are 3 monad laws which define what a monad is. These are not the 3 monad laws. The first monad law is you do not talk about monads. The second monad law is you do not talk about monads. And that is not actually the monad laws either. Don't bother about the monad laws. They're for mathematicians. The coolest thing is monads are synonymous with Kleisli triples. So if monad isn't impressive enough for you, you can actually refer to them as Kleisli triples. There's a German word and everything. It's completely confusing. So then what is a monad? This is not a monad. This is my use case for, I'm going to illustrate a monad. And this is actually an HTML document. What you're seeing is an ordered list, an OL tag, containing ponies and the corresponding elements of harmony. And I want to pick the elements of harmony out of this list without the ponies. So I have a function called children. Which takes a DOM element. We're into browser territory now, by the way. And it returns a list of these elements, child elements. So we get the ponies list. It has an ID called ponies, so let's see, just hold on. Let's take a look. So that gets us an ordered list, ID ponies, and it should have some contents. We can't see them. Let's use children to get the ponies. Yeah, those are the ponies. Now, the elements of harmony are child elements in this list. So, remember compose, right? Should be easy to get to compose children with an other children to get the grandchildren, right? No, because children takes one element and returns a list of elements. So you get some bug related to trying to use the one element as a list. Now, monads. We have something called the sequence monad. Hope I have time to type it out. A monad consists of 2 functions, unit and bind, to put it very, very simply, mind you. function unit simply takes one value, let's call it x, and returns a new value, which is x wrapped in the list that the monad is going to operate on. So it's an easy way of converting, say, an element into a list of elements. And we have the bind function, which takes a function with a value of any, sorry, with an argument with a value of any, returns a list of any. No, yeah, that function should return a list of any, sorry. So this is the function signature for children, incidentally. And it should return a function that returns a list of any. That takes an argument, which is the list of any, and returns another list. And we just did not fit that into one line. So I'm just going to, let's remove one space. Oops. So, and this should quite simply return a function that instead of taking one element and returning a list, it takes a list of elements and returns a new list. Which means that we basically have to, first the function, it takes, you'll notice, a list of arguments, and then basically just doing map on that. Because we have to make sure that we operate on each element in the list. It doesn't necessarily come with just the one element from unit. So, your traditional for loop. And we're going to concatenate, because we are going to get a list back from this function. So that should run a function that takes one argument and returns a list of arguments, concatenate the lists together, because we're looping over a list, and return the result of that. You with me? This is a sequence monad. And so, let's see, instead of composing children together with itself, we use the bind function that we just created. Because I don't know if you noticed, but the problem with trying to compose a function that whose argument is different from its return value is that it simply won't work, because compose expects the same type of argument to be returned as what is passed in. So we simply use bind to create such a function. It takes a function that has an element as its argument and returns a list of elements. And it produces a function that takes a list of elements and returns a list of elements, which is composable, right? What happens now? We get an empty list. Why? Because, remember unit, we're passing in a single element to a function that takes a list. And we simply use unit, part of the monad. And we get something that is not the elements of harmony, because the HTML structure of an ordered list is such that an ordered list with sub-elements, which the elements of harmony are, contains a new ordered list with list items. So we have to actually, instead of getting the grandchildren, we're going to have to go one deeper, like Inception. And there are the elements of harmony. So this was the elements of harmony monad, or in fact the sequence monad. And that's monads. Monads aren't, I'm about to say they aren't as complex as they sound to a room full of people who are a bit confused, I think. So you've at least seen what a monad does. It's basically taking a function and creating a new function that is composable using a certain type of monad. There's more than the sequence monad, but I'm not going to overwhelm you. That was monads. Now, very quickly, there's more. If you don't think even monads or Kleisli triples are sufficiently intimidating to the muggles, there's always more in Haskell. It's amazing the kind of things they come up with just to show off, in fact. Like isomorphic prepomorphisms. This is a real thing in Haskell, and this is all the documentation you get. I mean, when you think about it, if you're a mathematician, it's obvious, because it's a prepomorphism that has both soromorphic and isomorphic properties, right? This is how Haskell people get off, and it's quite beautiful. They're the worst kind of hipster. Of course, if even that isn't enough, there's always logic programming. And sometimes I hope our civilization is going to be mature enough that we can start using logic programming. So I'll see you in 100 years with a presentation on that. Thank you.